Hi, AP Calculus students. Welcome to section 8.7 on L'Hopital's rule. This is going back to limits, which I kind of like, right? Need a little practice, want to make sure we don't forget that. This is the easier way to solve some limits. Okay, and what I mean by that is there were limits that we solved using algebra or logic, or rationalizing the numerator, things like that. Turns out on some limits, there might be an easier way, and that would be by using L'Hopital's rule. Even though this rule has a quotient in it, and it also has derivatives in it, we are not using the quotient rule. We will be taking the derivative of the numerator and the denominator separately to use this rule. Okay, so here's what L'Hopital's rule is. If you have the limit as x approaches c of one function divided by another, it is equal to the limit as x approaches c of the derivative of the numerator divided by the derivative of the denominator, which can sometimes make an easier problem. If f and g are differentiable on AB, obviously they need to be differentiable for us to be able to take the derivative. The limit as x approaches c of f of x over g of x exists, right? So we won't be able to find a limit. If it doesn't exist, we can't force that to happen, and that happens sometimes, of course. The derivative of g cannot be 0, right? So, because of course we can't divide by 0. D, the limit as x approaches c of f of x over g of x is an indeterminate form. So you first have to use direct substitution into the original limit and see if you get an indeterminate form, meaning 0 over 0, right? That is indeterminate. We don't know what it is. You're welcome to argue with the experts on this, but we know 0 divided by anything is 0, but anything divided by 0 doesn't exist. And so which one of those rules overtakes the other, that is indeterminate. Okay, or if you have plus or negative infinity divided by plus or negative infinity, that is indeterminate what that answer is, right? Because, right, we have two infinities, right? And anything divided by itself is 1. Which rule are we using? It is indeterminate, okay? All other forms are determinate, right? If you end up with 12 divided by 0, that's determined to be undefined and approaching infinity, okay? You may need to rewrite the limit as a quotient. So if you have been given a quotient that is not, a limit that's not written as a quotient, but it seems indeterminate to you, if you can write it as a quotient, then you can use L'Hopital's rule. We're going to do that on one of these examples. You may apply the derivative one or more times. So if you take the derivative here and the limit is still indeterminate, right? That is a new function divided by a new function, and you are welcome to take the derivative again, the derivative of a derivative, until you can unveil the limit using L'Hopital's rule, or until you determine there's not actually a limit to find, okay? So here's our examples. 6b, the limit as x approaches -2. So let's go ahead and use direct substitution and put a -2, right? Because that's what we try with the limit every single time, right? So when I put a -2 into the denominator, I do get a 0. When I put a -2 into the numerator, that's going to be 8 minus 2 minus 6, which is also 0. So we do have an indeterminate form for this limit as x approaches -2. So according to L'Hopital's rule, what we can do is take the limit as x approaches -2 of the derivative of the numerator divided by the derivative of the denominator, and that will be the same limit if it exists. So the derivative of the numerator then would be 4x plus 1, and of the denominator, notice, would just be 1. Now when we use direct substitution, we do get a -7. If you in fact graphed this rational expression on your calculator and you approached an x of -2, you would see that graph approaching a -7. Let's do the limit as x approaches infinity of this expression. Notice we've done this, I think, in section 3.5. It may have been in chapter 1. Limits at infinity, right? Notice when you try direct substitution of infinity into the numerator and denominator, you do get infinity divided by infinity, okay, which is indeterminate, okay? Now, what we've done before, it's a rational expression. As you're approaching infinity, we have taken a look at the highest degree of the numerator and denominator. We do see that they are x squared, right, both of them. And so the limit should be 5/3, right? So you may be like, well, can't I just do that? Yes, you can. Yes, you can. But L'Hopital's rule does help make other limits easier. But let's go ahead and use L'Hopital's rule, knowing that we should get a 5/3 and see what happens. Let's take the derivative of the numerator and the denominator, and it's the same limit as x approaches infinity of 10x minus 3 all over 6x. Okay, when I try direct substitution here and here, I am still getting infinity over infinity, which means that I can take the derivative again, right? Because this is a new function. This isn't f divided by g. I can still apply L'Hopital's rule. So let's take the derivative again. I get 10 over 6, which is a constant, and that is 5/3. So isn't that kind of nice now that we know our derivatives, which we learned after limits, that we can now use them with limits too. Let's take a look at 8b. Okay, let's see, on 8b, it is the limit as x approaches 0 of sine of 6x over 4x. Okay, let's try direct substitution. I almost fell over. That was a little dance move, by the way. Let's try direct substitution of 0 here and here. Notice this would be sine of 6 times 0, or sine of 0 is 0, over 4 times 0 is 0. We do have an indeterminate form here, which means that we can try L'Hopital's rule. The limit as x approaches 0. I'll take the derivative of the numerator separately and the denominator. So notice the derivative of the denominator is 4. So I can tell already this will be a determinate form. Okay, let's see. Here I have the chain rule. The derivative of sine of anything is cosine of anything times the derivative of the inside function, which is 6. Let's now try direct substitution. Oh, can't put it into the numerator, the denominator there. This would be cosine of 0 is 1 times 6 over 4, 6/4 or 3/2. See, am I still on the board there? I am on the screen. Again, if you put this into your calculator as you approach 0, you would see the function approaching 3/2, even though it's not defined at x equals 0. Let's try 9b. Nope, we already did that. 7b. I had a particular order I wanted to do this in. On 7b, the limit as x approaches 6 of the square root of x plus 10 minus 4 over x minus 6. So let's try direct substitution here. When I put in a 6 here and here, 6 plus 10, that's 16. The square root of 16 is 4. 4 minus 4 is 0. And in the denominator, 6 minus 6 is 0. We do in fact have an indeterminate form. The way you knew to do this limit before was to rationalize the numerator, and you still can. You're welcome to do that. But I offer to you that we could take the derivative of the numerator and denominator separately and evaluate that limit. If it's okay with you, because I'm going to take the derivative, I'm just going to write that radical to the 1/2. Okay, so the limit as x approaches 6. Okay, let's see. Derivative of the numerator first, right? Let's see. So I'm just doing the numerator here. Let's do the denominator first, just because it's easier. I always do what's easiest first. The derivative of the denominator is 1, so that's nice. Okay, we won't have to worry about that. The derivative of the numerator, this is a chain rule. The derivative of anything to the 1/2 power is 1/2 times anything to the, I'll subtract 1 from the exponent, the negative 1/2. I will put that as a square root in the denominator, times the derivative of the inside function, which is 1, minus the derivative of 4 is 0. So this is actually now our new function, our new quotient. And when I try to substitute in a 6, I can now evaluate the limit. 6 plus 10, again, 16, square root of 16 is 4. This is 1/8. Again, this limit does exist. And apparently using L'Hopital's rule, or you could use rationalizing the numerator too, it is 1/8. Okay, let's try number 46 and 48. Okay, on number 46, let's take a look. The limit as x approaches 0 from the right of x cubed times cotangent of x. Okay, notice we can try direct substitution of 0 because the limit as x approaches 0 is from the right and the left. So I can still use direct substitution even though it's only from the right. Can I have a little sip of coffee? So let's take a look here. Let's try direct substitution of 0 here and here. That would be 0 times, right, because that would be 0 cubed. The cotangent is 0? I'm not sure. Let's do the tangent of 0 and then take the reciprocal. Okay. Tangent of 0 is 0, right? And so the reciprocal of 0 is 0 over 1. So the reciprocal would be 1 over 0, so it's undefined. I don't know what is 0 times infinity. 0 times anything is 0, but I also have anything times infinity is infinity. So what I think I want to do, I think this might be an indeterminate form. And so what I'll do is write it as a quotient instead so that I can use L'Hopital's rule, right? So let's try that. Let's see if this is an indeterminate form. And what I'm going to do is notice I did say it was 1 over tangent, like I already made it a quotient. So this problem, right, this expression is the same as above. Okay, and then when I try direct substitution, I get 0 in the numerator and tangent of 0 is 0. This is in fact indeterminate in quotient form, 0 over 0. So let me try taking the derivative of the numerator and the denominator and seeing if I can unveil a limit. That would be 3x squared. The derivative of tangent is secant squared. Okay, let's try 0 and 0 and see if we get an indeterminate form. So in the numerator, that's 0. Now secant squared, secant of 0 squared, unsure. And so I always write it this way for myself. Secant is 1 over cosine. So that's still secant, and then I'll square it. So when I put a 0 into cosine here, cosine of 0 is 1. 1 over 1 is 1. 1 squared is 1. So that numerator, that denominator is actually 1. 0 over 1 is determined to be 0. So there was a limit and we found it. Writing our expression as a quotient and using L'Hopital's rule. Last one, number 48. Okay, on number 48, let's see. The limit as x approaches infinity of x times tangent of 1 over x. Okay, let's try direct substitution. Right, we get infinity times. Now, 1 over infinity is 0, tangent of 0 is 0, okay. I think we're running into an indeterminate form, but I can't use L'Hopital's rule in that way. It has to be written as a quotient. So what should I do? Well, I don't want to write tangent as the, as cotangent in the denominator. I'm not really a fan of using reciprocal functions. I like my sine, cosine, and tangent. So this is where I see a pattern here. I do see a 1 over x in the tangent. I can't take the reciprocal of that. I can only take the reciprocal of the trig function. But I can take the reciprocal of x, right? This is x over 1. How about, see, since I see tangent and the angle is 1 over x, what if I write x over 1, if I write the reciprocal of that and put it in the denominator as 1 over x? This may look more complicated, right? But I think it's actually going to help us because we kind of have a match here. So take a look, tangent of 1 over x, I could either divide it by 1 over x or multiply by the reciprocal of x over 1. I have the same expression here as I do above. Let's check out when you put in infinity. Again, we said tangent of 1 over infinity is tangent of 0, which is 0, and 1 over infinity is 0. We now do have an indeterminate form in quotient form. Let's take the derivative of the numerator and the denominator. All right, so the derivative of chain rule here, tangent of anything is secant squared of anything times the derivative of the inside function. This is 1 over x. I could write that as x to the negative 1. I'm going to take the derivative of that. I'm going to bring the negative 1 out front and multiply it and reduce the exponent by 1. That's x to the negative 2. If it's okay with you, I'm going to write that in the denominator as a positive 2. Okay. Again, the derivative, I already did it, of 1 over x is a negative 1 over x squared. So look what happens here. Notice that now the negative 1 over x squared cancels from the numerator and the denominator. So now I'm just trying to evaluate secant squared of 1 over x. Okay, so let's try that. I write this as, again, not super good with secants. So I'm just trying to make sure I still have room for you here. The limit as x approaches 0. Can you see? Yes, you can see that. Secant, I'm going to write as 1 over cosine. My angle is 1 over x, and it's being squared. So if I take, this is still secant, right? 1 over cosine of 1 over x, and then I square it. Let's put a 0 in here. Okay, notice that 1 over 0 is undefined, right? And it's undefined. Where is cosine undefined? I really felt, let's see. I really felt I had this right. I'm going to hit pause for a second because it's the end of the video. And if I made a mistake, I don't want to have to redo it. Hold on a sec. All right, class, I see what I did wrong. Luckily, it wasn't a mathematical error. It was the limit as x approaches infinity here, in here, and here, and here. Somehow I switched it to 0. So sorry about that, but our math was just fine. Okay, so let's take a look here. So I did have the right limit here, x approaches infinity, and did get the indeterminate form. And then here, okay, I did the derivative correctly, right? And then when I went to do my substitution, I'm like, no, I know there's a limit. I picked 1. Okay, it was infinity. Okay, 1 over infinity is 0. Cosine of 0 is 1. 1 over 1 is 1 squared. And so we get a 1 here. So there we go. Whew, could have used some more coffee on that one, I guess. All right. I hope you enjoyed L'Hopital's rule. It's the last thing you are learning before your winter break. Have a good day.